All right, so we are doing 4-2A. You can do the warm-up on your own. That's just from the 4-1. Binomial distribution. So binomial means 2. So in this case, it's basically just you are running an experiment and you are just reducing it to 2 outcomes. You either get what you want or you don't. You succeed or you fail. So we don't really care about anything else. It's either you like if you're trying to roll a 6, you either roll a 6 or you don't roll a 6. That's it. We don't care if you get a 5 or a 4. Like, that doesn't matter to us. We just care you got it, or you got what you wanted, or you didn't. So that's a binomial distribution. Each trial, it can be reduced to 2 outcomes, a success and a failure. You get what you want or you don't. So these are the things that have to happen in order for it to be binomial. It has to be repeated for a fixed number of trials. So like, you're going to roll the die 10 times and see how many times you get a 6. You're not going to roll it until you get a 6. You're not going to roll it just until you get 12 6s, whatever you want. You're just going to roll it 10 times and see how many 6s you get. So the set number makes a big difference. 2 possible outcomes, a success and a failure. You get what you want or you don't. The probability for success has to be the same for every trial, so it can't change. So if you're doing cards, like, you have to put the cards back after every try. Your probability can't change the second time because there's fewer cards in the deck. Like, you have to continue to replace things so that that probability stays the same throughout all of your trials. And then your random variable x this time counts how many successful trials you have. So how many times do you get what you want? So these are the things that we're going to be using, n, p, q, and x. These variables, n, p, q, and x, we're going to be identifying a lot. So n is how many times your trial is repeated. So how many times are you going to roll the die? How many times are you going to pick a card? Whatever it is. That's the set number. Your probability for success has to be the same. So if we're trying to roll a 6, like, our probability for success is 1 out of 6. Okay, you have a 1 out of 6 chance of getting it. The probability of failure is the rest of it. It's the complement of success. So your success is 1 out of 6, then your failure is 5 out of 6. Okay? And then your random variable counts how many successes you have. So did you get what you wanted no times? Did you get it once? Did you get it twice? Those are all the different possibilities of how many times you can get what you want. So from a standard deck of cards, you pick a card, decide if it's a club or not, and put it back. You repeat the experiment 5 times. So all of this is important. You put it back. You replace the card. So that means that the probability stays the same throughout. Okay? You repeat it 5 times. So there's your set number. All of this is making it a binomial experiment. And then it says you can be classified in 2 categories, which is your last criteria. Selecting a club is your success, and then picking anything but a club is your failure. Okay? So we're being asked to identify n, p, q, and x. We're going to be doing a lot. N is how many times you repeat it. So we do this experiment 5 times. So we have 5 different chances to get a club. Okay? My probability for success, I'm trying to pick a club that's a quarter of my deck, or 13 out of 52. As far as we're concerned, we're going to be using these in using these numbers in bigger formulas. So the more you can reduce your fractions in these cases is probably better. So 1/4. Your q is your probability of failure. So that's 3/4 of your deck. Okay. Remember, your p and your q together, they add together to give you 1. Okay, they're a whole. They're 100% when you're done. And then your x is your probability, or like how many times you can have a success. This doesn't tell us how many times we're succeeding, but we know we could do this 5 times and not pick any clubs. We could pick 1, we could pick 2, we could pick 3, we could pick 4, or we could pick them all 5 times. Okay? But that's it. Can't pick it more than 5 because I'm only doing 5 trials. So those are all of my possibilities for x. Okay? And then that's it. N, P, Q, and X. All right. Surgical procedure has an 85% chance of success. So that doesn't change. It's not like Doesn't worse the second time they go to do it. Okay, they always have 85% chance. A doctor performs the procedure on 8 patients, so there's your set number. The random variable represents the successful surgeries. Okay, so is it binomial? Yes, because we have a specific chance or the probability for success is the same. We have a set number, and it either succeeds or it fails. Those are our 2 things. So N, how many times is he trying this? He's doing this on 8 patients. P, probability for success in this case is 85%, so 0.85. Q is your probability for failure, so he could fail 15% of the time, right? Together, remember that Q is 1 minus P. Okay, so 1 minus 0.85 is 0.15. And then X are the possibilities of successful trials. He could have none all the way through 8. Okay, so he could have no successes. He could have up to all of them be successful. Now, obviously the probability of him not having any successful trials is going to be really small because it's an 85% chance of success. If he does this 8 times, the probability of none of those working is going to be really small. The probability of all of them working is going to be a little bit higher because 85% is closer to 100, right? But that's still not as likely. So the other thing we have to do is kind of figure out what's the probability of 5 of them working. What's the probability of 2 of them working? So we're finding the probability of a specific number of successes. And that's what this next giant thing is for. Okay? You can kind of ignore all this stuff over here. It doesn't really matter. The formula part is here. Okay, so there's your formula. You can copy it down, and we're going to use it on the other ones. But you know how to find all these variables, so don't let it freak you out. We know how to find N, P, Q, and X. Okay? And then you just fill them in. There's something on my screen and it's driving me crazy. All right. So here's our formula. We're going to talk about where all these numbers came from. A 6-sided die is rolled 3 times. Find the probability of rolling exactly 1 6. So my N, how many times am I going to try? 3. My probability of success, what's the probability of rolling a 6? 1 out of 6. Q, what's my probability of not rolling a 6? 5 out of 6. And X, this time I know what it is, exactly 1. Okay? I want to have a successful trial once. I want to know what the probability is of only getting that success 1 time. Okay? So that means that I have all of my variables for this formula. Okay? We just said N is 3, so I just fill them in. 3 factorial over. And again, it's 3 minus, I want 1 successful trial. Another 1 with a factorial. My probability of success is 1 out of 6. My probability of failure is 5 out of 6. I just had to fill in those exponents. My X is 1. My N is 3, so 3 minus 1 is 2. Okay? Looks way worse than it is. So that's where all those numbers came from. That's what we already have. I would suggest doing this fraction first in your calculator. So you would do 3 factorial over 3 minus 1 is 2 factorial, 1 factorial. Okay, all together on the bottom. Put that in your calculator. When you do that, you get 3 in this case. And then 1 6 to the first and 5 6 squared. And then you can just put all of that in at once. And we get 0.347. So there's about a 30, almost 5% chance that you get 1 6. So you roll a die 3 times. There's a 35% chance that you're going to get a 6 one of those times. Okay? Not 2, not 3, but once. All right, a card is selected and then replaced. So we know that we have the same probability for success for all of them because you put it back. It's repeated 5 times. Find the probability of exactly 3 clubs. So we did a lot of this already. So our n, how many times are we trying this? 5. The probability of getting a club is 1/4. The probability of not getting a club is 3/4. The only difference is that now I know what x is. I want to know exactly 3 clubs. So my x is 3. So then I take these and I plug them into my formula. Okay? N is 5 factorial over, again, 5 minus, I want 3 successes. So that's my x. X is still 3. My probability of success is 1/4. My probability of failure is 3/4, and I just fill in my exponents. So my x was 3, and then n minus x, so 5 minus 3 is 2. Okay? Simplify your bottom before you put in your calculator. So 5 minus 3 is 2 factorial, and then that 3 factorial. You want to keep them together on the bottom, and then put those in your calculator. So 5 factorial divided by parentheses, 2 factorial, 3 factorial. Close parentheses, you get 10. So from that fraction, I got 10. So then I'm going to do 10, and then I'm going to do 1/4 to the third and 3/4 squared. And I can put that all in my calculator at once. So 10 times 1/4 to the third and 3/4 squared. 0.088. Small. So I have less than 9% chance of picking 3 clubs. Okay, so I pick 5 different cards, and I have less than 9% chance of 3 of those 5 being clubs. Okay, that's pretty small. All right, so binomial distribution, a chart that's all the possibilities of x. Okay, so if I go back up here, that would be, instead of like exactly 3 clubs, I would have a chart where I would repeat this formula for all the possibilities of x. So I could pick 0 clubs. I could pick 1, 2, 3, 4, or 5. So I would have to do this formula for all of my possibilities of x. Okay? So this says, in a survey, American workers and retirees are asked to name their expected source of retirement incomes. 7 participated, so there's your N. 35 said they would rely on Social Security. So your probability of Social Security is 35%. Okay? So then your probability that they do not rely on Social Security is 65%. And your possibilities of x are 0 through 7. Okay, because they none of them all the way through all of them. And this says use a binomial distribution to find the probability for all your possibilities of x. So you would do that formula 8 times to fill all those probabilities in. Okay, notice the extremes are the smallest. For nobody to say it, and then for everybody to say it, those are the tiniest. And then they kind of skew towards whatever your probability is. So the probability is only a 35% chance, so that's pretty low. So then the bigger numbers are on the lower end of my binomial distribution. Okay, you have to repeat that formula 8 times to fill this in. Okay, all right, for 2A.